You hear me?
Yes.
Yes.
Very good. So, shall we start?
Yes, we can.
Are you ready to start?
Yes.
Very good. So, we shall start with exercises, as usual. So, this is what is, sorry, I just want to make correct photos. So we start with exercise, excuse me, sorry. Do you see the sheet of exercises?
Yes.
Very good. So we were studying the group, and we defined the group as the fundamental group of the complement, of the not complement, but it is also possible to write directly the Wirtinger presentation. Maybe I make it larger. It's better. So Wirtinger presentation, and then use, as we used, for example, for coloring, use Reidemeister moves and then obtain, without making reference to algebraic topology, that this group is invariant of knots of links. So let us start. For example, we were doing this, excuse me, I'll try to make it bigger. Oh, it's okay. You see the exercise? Rafael, do you see your exercise?
No, I do not.
What do you see in your screen?
The exercise sheet, but not the solution.
Me. And now do you see, no?
No.
Mm-hmm. Okay, I'll try now directly from email. So I don't know why the photos is not given, so I try directly from email.
Maybe you are sharing only the internet window and not the whole screen when you started to share your screen.
Do you see now?
We see the Gmail page.
No, that's not good. Okay, I see now. You can see. Okay.
Yes, yes, we can.
So we were doing this last time.
Yes.
So there are two. Now let us look at your other. No, it's previous one. No. Don't see. Sorry. No, I don't know. Oh, okay. Do you see now?
It's not the good exercise. It's an old one.
The third one?
No, it's an old one from last lecture.
Mm-hmm. Mm-hmm. Sorry. You see?
Yes.
Okay. This is, yes, finally, sorry. So this is here that you have, Raphael, X and Y, okay? And you denoted, this is old X, this is Y1, Y2, Z1. Can you continue, please, your solution?
Yes, so then we write each intersection point, and we write the relation between the arcs at the intersection. So there is 1 and 2. The first one, the relation given is y1 x z minus 1 x minus 1, because we go around counterclockwise.
Right?
And then we write the relation for the second one. So x z x minus 1 y2 minus 1. So it gives us that z is just equal to x minus 1 y1 x in 1. We make the change in one.
Mm-hmm.
And then we can just eliminate z. I mean, we substitute z in the second equation.
Mm-hmm.
And so then we got just that y1 equals 1, 2, y1 equals y2, and this is exactly the same as the same representation as we had before, the old one. So it doesn't change the group, this Reidemeister move.
So this is formally this is called the Tietze transformation. You
Yes.
write down this letter. This letter is expressed by the other letters, and then you can substitute and then erase this this letter, because this is the legal Tietze transformation, and then you get that taking finally you get that in your suppose that here you have previous part of relations where x and y is involved, and then finally we get rid of z and we get y1 equal to y2, because here, if you look, there should be relations with y2, right? Because it may be another Vertinger crossing and so on. And now you see that if you should always have in mind that Reidemeister, and we see today in skein relation that you should look at that you are looking by microscope. This is only the small part of our knot. They may be the crossings and relations. Here is this x involved, here is y, and here is y. Here the same relation, only with y1, only with y2. And this is very good, this is very essential, that having these Tietze transformations, you really obtain that y1 is equal to y2, because here there should be relations with y1 and relations with y2, and when you are getting this thing, you having the same list of relations which were here, where y is involved. So this is the same group, only different presentation. Right. So other questions, remarks, dear friends? Natalia, do you agree with this?
Yes, I agree.
Thanks. So now we shall look for more. This is yes. This is the I remind, and today we'll see again this relation, this Reidemeister move 3. It will appear in braids. So here, what do we have here? Okay, let's start. So can you do this?
Yeah, so we want to show that the representation on the left and the representation on the right is actually the same. So on the left, we write each representation at each crossing. So there is one, big 1, big 2, big 3, and we do the same on the right. So the first remark is that crossing number 1 on the left and crossing number 3 on the right are actually the same. So we just need to focus on crossing 2 and 3 on the left and crossing 1 and 2 on the right to show that they are the same. So then if we look at the relation on the left, by taking relation number 2, we eliminate the letter E, and we rewrite we take relation 3, we eliminate E, and we rewrite relation number 2. On the right, we eliminate G by taking the relation number 2, and we plug this new relation in relation number 1.
Excuse me, can you say it again?
Yeah, sure. On the right, for the right one.
Yes.
So for the right one, we substitute G. Or we write that G is equal to TDC minus 1.
Right.
So it's relation 2. And
yes,
then
this is incoming, right.
Yeah, so because we are deleting G, eliminating G, we rewrite relation number 1 on the right.
Right.
And then we just need to remember the relation A minus 1 C, B, C minus 1. And we see that actually this relation, so wait 1 second. So we see that this relation here and here are actually the same by taking this relation into account. If you scroll down a bit, it's maybe here.
Right.
And we are done.
So this is actually you have see here that there are new there are different letters. You see that here is A, F. So the same are A, F, B, D, but here C also. But here is E, and here is another one, G. So
that's why we eliminate them.
Yeah, the nature of them is different. C is between F and C, and G is between D and A. So this is quite different, but we need to eliminate, and then we apply, and then we get. Okay, very good. Other questions, remarks for this exercise in calligraphy of writing letters? If there are no remarks, I try now to what do I try? I try to get sorry. So this sorry. Okay, sorry. I don't know why it disappears. It disappears and appears. Okay, so This exercise, the exercise number 2, is crucial. I'm sorry, you don't see the screen?
No, we don't.
Excuse me, I'll try now. I see that I try to do this again. To do the screen. Try again. No. You see now?
We see the exercise.
Yes.
Not the solution.
That's what I want to say, that why this exercise is also important. The first one is important in the sense that it gives a proof that the Vertinger presentation is invariant of links. And exercise 2 is interesting that the group is not complete invariant. We shall see maybe next time when we'll study, when we look at the Jones polynomial, that the value of the Jones polynomial for right-handed and left-handed trefoils is different. So, and now this is exercise to see that, however, the group, the Vertinger presentation, and also the right-handed and left-handed trefoils, they are the same. So you can't distinguish the two trefoils with the help of the fundamental group. So, where is Raphael? Can you remind me your calculation? How did you do this?
Actually, it was I just wrote the arcs and it just got the same straight away with no complication at all.
Yes, but yes, but the so at what level maybe you can, I don't see your, where did I put your sorry. You send me in the same email?
Yeah, all together.
All together, right? So I don't see where I. This is exercise 2. How did you, or exercise 1? Okay, sorry. No, this is 1. Exercise 2, right?
It should be exercise 2. Exercise 2.
No, this is previous one. This one?
I don't see anything.
This one? No?
I don't see the.
Ah, you don't see it. Very good. See?
Yeah, this one. Because in the class we already last week we already did during the lesson.
Right.
So here I just wrote the arcs and just
and so you have the same presentation at this level, right?
The same as in the class, yes.
Very good, very good.
Yes, I think about this problem, and if we reflection left default, we have right default.
Mm-hmm.
And if we reflection by plane xy,
Yes.
we change point up this plane to
Mm-hmm.
point down this plane.
Right.
But we can change point, first point for our group. And we
Right.
have, this is the same group.
Yes.
Is it
This
right?
is by definition. You are right, Natalia, you are right, because this is exactly the the definition. Whether you understand this by geometry, as you say, reflection by the plane, or if you are looking at the level of diagram, you simply change crossings. You simply change crossings when you have this type and this type, but when you construct Vertinger presentation, you see that the presentation will be the same. So, right, exactly. By the definition, the not mirror image is defined this way: either reflection by the plane xy, or simply changing. If you don't want to look at geometry, you are simply changing the crossing in the points, and that's all. Very good, very good. So this is done. What do we have next? Excuse me. Again, I need to exercises. So the aim of the next exercise is very close to the fact that we were studying the torus knots. So the torus knots. Sorry. Right. New, where it is. I don't see them. Right. So the presentation of the cinquefoil. So I again need to find the sheet, and so this we can eliminate now. So the sheet I need to find, sorry, the sheet. So this one, right?
Yes.
So you see now, right?
Mm-hmm.
The cinquefoil, you see?
Yes.
Yes.
Very good. So you wrote down 1, 2, 3, 4. So this is cinquefoil. You see and I want to have you the final. Sorry for that. So you wrote down in this form.
Yeah, I didn't make the change with. I think we can make a change with A equals TY, probably something like that, and use some power, if I'm not mistaken.
Right. So that's usually, and why I gave this exercise, because we'll get the presentation for all the torus links. So actually we need so cinquefoil, by the way, cinquefoil, what it is, how can you describe it as torus knots? We were looking at torus knots. So it is, what are the numbers for the cinquefoil? So it goes in one direction. How many times it goes? 1, 2, 3, 4, 5, right? And only two times in one direction and 5 times in other direction. So cinquefoil is T225, right? So
wait, can you say again, what do you mean it goes 5 times in one direction and 2 times in the other? What do you mean?
This is what I meant. Right. So, excuse me. I should remind our previous lectures. So we should, excuse me, I always coming back to this one, but I need to have what is this? No, this is maybe in the right. So this is our construction of torus link, right? You have maybe for the cinquefoil, I can write this one. So maybe we'll start for the me. It's very bad. So the picture that I made. So we were considering cinquefoil. What does it mean? That it should be 2 times here and 1, 2, 3, 4, 5 here. No. So you should do this, and then sorry, I'm very bad in writing today, especially. Anyway, so it no, let it be for trefoil. I'm trying to be very accurate. Right? So let us do like we'll consider 3 times here and 2 times here, right? So this one and here you have 1, 2, and this is 3. No, I'm very bad. Sorry. Maybe I'll, so I'm very bad in writing. Me. So maybe I'll try to explain this in the picture that I made for the next exercise, so it will be better. Don't know how to. So, do you see my picture?
Yes.
Yes.
So, this is at first look at the lines which are black ones.
Okay.
So forget about red ones. So suppose that this is a torus. So this is the square with identified the edges. So we have what we are doing. This is 1 and this is 2. So we are making so here 2 parts and here 3 parts. So this is line which has the tangent 3 to 2, right? So you make this line like this. Okay? Then you came back here because you are in the torus, and again with the tangent 3 to 2. So here it is 2. This is maybe 1 centimeter. And here you have 3. So you are going this way, then you are going this way. And then what does it mean? You are again here, and again with tangent to 3, you are coming here. And you came here, and finally you return. So this is the trefoil on the torus. So imagine that this line is equivalent to this line. This line is glued with this line. So you can, this is a typical picture of trefoil, right? So it takes 3 parts here and 2 parts here. That's what I mean by, for example, if you have, for example, here, make somewhere here, it is this line in the torus. This will be the circle. This will be the circle in the torus. See how many points does this line meet our trefoil. It means 2 times, here and here. And in any line parallel to xy, it meets our, here for example, and here, it meets exactly in 2 points. But if you consider this, suppose this is a meridian, and this is a parallel, right? So calculate here, 1, 2, and 3 points. So if you now make the picture of torus, I don't have space here. Okay, I'll try anyway. So if you consider now that you are in torus, what do I mean? If you now write down the parallel of this torus, so this line, anyway, let it be this line. So you see that you're not meets parallel sorry, in 3 points, right? Meets in 3 points. But if you now take a meridian, if you take, no, just consider meridian. So it will be 2 points. So if you now depict meridian in your torus, you see that your node meets meridian only in 2 points. That's what I meant, and this is the answer to your question, Rafael. Is it okay?
Okay, it's clear. Yeah, it's clear. Thank you very much.
Very good. Very good. So now, right. So what I in the picture that you were giving us, sorry, where is your screen? No, this is not what I wanted to do. So I actually wanted that we should obtain the following, as you saw that this is the SENC foil. So in our no, this is not what we want. So the same way you can do. So as I make this terrible picture that 2 parts here and 3 parts here, you can make 2 parts here and 5 parts here. So our picture for the SENC foil should be something like this. Should be something like this, more like this line. Maybe line this. So you should meet again 2 times here and 5 times here. This will be our SENC foil. And the presentation that actually I wanted to have is the following: that you have one, say, A2 is equal to, with 2 generators. That's why because you know that every group have infinite number of presentations. But for SENC foil, I wanted to have this presentation. And actually, today, I hope we'll prove the general fact. This will be our first goal for today, to prove that for torus nodes that we have RQ, one of our consideration today is to prove the following formula, general formula here. So, and this will correspond very good to our torus node that we have A2 equal to B3. The torus nodes that you were considering, you should get this beautiful formula. So, but I remind that this group is not commutative, so there is no relation that AB is not equal to BA. Is in this non-commutative group. Anyway, you have the only this relation. What does it mean? That if you have word, say A, I would say it could be B. This word is equal to word B3 AB. But it doesn't mean that you may change. So you have group, it's not commutative, you should have the words. Of course, in your words you may have say here again A minus 1, right? And say here also A minus 1, have equality, right? So you consider all words of A minus 1, B minus 1, with evident identities that A minus 1 is 1, B minus 1 is 1, and plus you have this relation. That's all. Sorry, no, this relation. So this will be goal for us for today. Okay, so now we return to our link, because we are studying torus things. We return to links. Okay, maybe this let it be. We return to links. So this is the exercise for the torus links. You see that when you are making picture like just one line with tangent M to N, Q to R rational, then you have not. But in our picture, we were sorry, we were looking. No, this is the same. Sorry, right. So returning here, but when you put here if you have put here 2 and you have rotation angled 3 pi, then you will have our trefoil. But if you put 4 edges, then you have 2 trefoils and you have the same rotation. Then you have 2 trefoils and they are linked. So our first work is how calculate the linking number. So remember how we were calculating using the orientation and crossing point, and in crossing point either 1 or -1, and then we get the the linking number. So who can calculate this linking number for T2 to 6? That this is the question. So who can calculate this?
I can.
Can you show us, please, Natalia? I was sure that
I cannot.
Ah, you cannot. So Rafael, can you?
So wait, if we look back at the picture you had.
Yes, I try to return now. Sorry. I'll try to return to this picture. Yes. So sorry. So Natalia, you should now look at both. You should look both at the black one and red ones, right?
So if we do the same reasoning, we take one big circle and a meridian. So what do we have?
Yes, but to have a diagram, I propose you to. This is on the torus, right? But yes, there are no intersection, no diagram, no projection. So to get a projection, first of all, you should.
No, because my idea was to look on each line what kind of intersection we have with the meridian. For example, if we look here, and let's look at the black one, we have 3, right? If we just focus on the black one, we have 3, and yes, if we look on the other one, we have 2. Now, by looking at the same for the red, with the red, we have the same result. We have 3, 2. So it looks like we have 2 trefoil again.
Mm-hmm.
One in the other, looks like.
Uh-huh. But I propose you to obtain the diagram from this the following way. You consider this is a torus, right? So yes, it is quite far from the sheet of paper where it should be. So just make a, I forgot the English word, maybe Raphael take it. Plié.
Fold?
Fold, right. Fold. Natalia, согнуть. Just to make
like that?
This.
You mean?
No. Just consider this piece of paper and you double. You double the, so you put this one, so the same way maybe I show you in the I should take a small piece of something. So if you have, do you see me?
Yes, yes.
Yes, yes.
So you have something like this, and you make this one. Okay. So this part I double.
Yes.
This part I double. I put it under. I put this part under. You see, and these dashed lines means, for example, here you have real line on the torus. But when you have another sheet, it is, I noted it by dashed lines, either black ones or red ones, because they are and to indicate. Of course, for the diagram, it's also okay, because this part, if you look at this projection, it will be so this will be overcrossings, and these guys will be undercrossings. So, but this is not all, because here you should identify this point with this point. So how should I do this? I can now glue some band or ribbon, and glue this ribbon here, and I have a projection. So formally, the statement that I'm saying is the following: that if you make this line, which line somewhere aside this part of circle, here actually 4 parts of circles, 2 for red, and also I draw badly. This is for black one. Excuse me. This part is out of business. This gives you the diagram. This is a real diagram of our link. Okay, so you have these guys, which are overcrossings. These are because they are on the other side of our sheet of paper. They are undercrossings.
Sorry.
And in order to make identification, you are making this identification by some lines which don't have crossing. I'm looking. So Natalia, what is your remark?
Sorry. Can we fold by vertical line?
Yes.
There's a horizontal line and vertical line, and is it not true?
You can do, but our aim is to get a knot diagram, and by definition, knot diagram is given at the plane. And if we made, for example, only one this folding, right? And then you are proposing to identify this with this, we'll get our diagram at the cylinder. Of course, you can consider the projections of your nodes on the cylinder, but this will be another story. You should develop the theory. I read something that you can make projection on torus. This is quite popular because of the grid presentations of nodes and so on. But our aim, and for example, how we were defining the linking number. The linking number we were defining. You take the projection on the plane. You consider crossings. You consider plus minuses, and you get your linking number. Maybe it will be okay with your projection to the cylinder. In this case, I think it works pretty well, but in general, I don't know. So we need to have projection on the plane, and this is the real node diagram on the plane on the sheet of paper, right?
So wait, just again. So we have this square, not the torus. We write the line, then we fold this square, and we see the intersection, right?
Right. Exactly.
And then
you see, look, for example, when you are folding this line which was going up, it goes down.
Yes.
And it exactly. So in the torus, you see that this point is equal to this point. But in this link projection, it is by the construction of our projection, this point meet. And the same happening with this point. So this point, which is on the torus, you should identify. By this projection, they are identified by the construction.
Okay.
The only subtle point is to identify this one, for example, with this one. But suppose that this point is made from rubber, and you are making this point a little bit longer, and it goes here. But so topologically, it's actually the same.
Okay. Yes. Okay.
Natalia, you agree?
Okay.
Very good. Very good. Then linking number. So what do you, for example?
I have a question about this picture.
Yes.
Can I this is my my rectangle, and this is my torus. I picture in line in this rectangle, and can I
yes, the direction doesn't matter. Yes.
And this, and put in my plane, and I have projection. Why not? Maybe I can. Maybe I have not simple cross, but if we have Okay, maybe our crossing line is not one-to-one. Maybe this is a problem. Okay.
Yes, okay, so we should think about it, but
But if we cannot cross 4-line or 3-line, only 2 lines, we have a projection in
yes, yes, I think yes, because you can cut your torus and then this. So suppose that you cut your torus like this, then you have the lines on your cylinder, and then you just smash this cylinder, and you have real projection of the cylinder at the
Yes, but
yes.
we can this projection, but we can end this projection. This not same.
Yeah, this is not the same.
And
Yes.
we can this and this projection at the same time, and we have a projection.
Yes, but it is maybe more complicated. I can answer immediately at your. So you maybe it's okay, but maybe you have some extra crossing. I don't know.
Yes, it's
I don't know.
It is a problem. Yes.
Yeah.
But if for several number we have a projection. Okay. Okay. Thank you.
Yes. So, and if you now agree with then we simply calculate. Remember that how we were calculating the linking number. You should consider projection. Say, so what do you prefer? So we need to say, what do you prefer? Calculate the red with respect to black or black with respect to red? Tell me.
Let's say black with respect to red, for example.
Sorry, red with respect to black, right?
Yeah, okay, that's cool.
Okay,
Is
so
it our torus 6-4? Is it 6-4?
yeah, yes. So you can verify here 1, 2, 3, 4, 5, 6, and if you calculate here, you have 4. 1, 2, 3, 4, right? So it's 4 crossing here, 6 crossings here. So it's visible. So if you now take red, you should take into account only crossings of different colors, because each crossing, for example, we saw the black one, it has the proper crossings which correspond, because each of them is trefoil, and you can have this crossing, you can calculate Wirtinger and so on. But to have linking number, you have to consider different crossing. The crossing of the red with black. So how many they will have? All of them will have the same sign, as far as I understand. So this one, this is, for example, here. If we consider this one from positive to negative, from red to black, we have from so here all of them will be from red. Excuse me, maybe I'm wrong. So this is red one, right? This is red one, this is black one. So you have here -1, right? So here you have again -1. Here you have again -1, so positive here, positive here, you have -1. So how many crossings? You need only to see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? Am I right?
Yes.
So divided by 2, you have 6. The crossing number is 6. Am I right?
Wait, so the sign is minus or plus?
Yes,
here?
sign is minus, but you can change
yeah.
it. You can change it with no problem if you change the direction. If you don't like minus,
yeah.
you can change direction for the black one, for example. Change this opposite direction, and I suppose, is it okay if you change direction? Yes, if you change direction in this one, then you have the positive. So the sign depends on the orientation. So if both of them are positively oriented, then it's okay. Yeah, but no. I think you are right, because positive, they should both of them oriented in the same way. No. You are right. You are right. The sign matters. All of them should have in the same direction. Then it is positive. No. Very good. Very good. Then yeah. So it's not by chance that I took. If we take, for example, this cylinder, all of them should go in from bottom to up, and then we have yes. So this is exactly will be -2. The linking number will be exactly -6.
-6, yeah.
-6. Yes, it's okay. Is it okay? -6. Oh, so maybe we shall look. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yes. It should be -6, right? Linking number is -6. Well, now, Natalia, you are the best of us to construct Seifert surfaces. So can you explain for us Seifert surfaces at this picture? How many how many pieces of dimension 2 and how many edges. Or you can directly, I saw you like graphs, so you may directly explain us. No. First of all, tell us the pieces of surfaces and then how they are connected with edges. So it's here in this diagram. That's why I draw this picture, because it's clear how you construct the affect surface. Natalia, are you with us?
Yes, I think.
So look, for example, for example, this one, the big one, okay? Start with, for example, from here. What do you see? You see like this, okay?
Yes.
This will be the biggest sheet, right? 1 point, okay? Then take the second point, which are going here. What do you see? It is going like this one.
Yes, this line is a second circle.
Right. Excuse me for my bad writing. So this is another point, or another sheet of so you can consider it as a piece of paper, right? Then you see how beautiful this will be, sorry, the third one, right? And then finally you have the fourth one. It's too thin, my drawing is very poor. Okay, so you have 4 pieces of paper,
Yes.
right?
Yes.
And so this is dimension 0, then this is 4. Very good. So how many crossings? How many crossings?
Many crossings.
But so we are developed enough. We can count more than fingers, right? So how many crossings? My picture becomes terrible, but
Yes.
so
1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. 6 in upline and 1, 2, 3, 4, 5, 6, 6 and 6 and 6. 6 by
so in each line you are very good. You are very smart, Natalia. You have 6 crossings here, 6 crossings here and 6 crossings here, right? So can we multiply 6 by 3, right?
I think 6 by 4, no?
By 3, by 3, right?
Down and, okay, it's a different point, okay, yes.
You have 4 points, but between them there are 3 intervals, right? So this will be minus 3 times 6. It will be 18, right? And this equals to minus 14, right?
Yes, minus 14.
Yes, and sorry, for the our calculating of genus, our formula was what? 2 minus.
I think it is not right. We have 14 is even, but it's not right.
It's right. I'm sure it's right. Why? Because we have the formula, and if you are looking at the...
No, we can plus 1, and we have 2 minus 2g.
Right. And minus 2.
It's not equal.
And minus 2, Natalia. The formula for genus now becomes 2 minus 2g minus 2.
Yes,
Why?
but 14 plus 1, 2g minus 2. We have 4 vertices,
And
18 edges, and one face, and we have 2 minus 2g. But if we have 4 vertices and 18 edges, we cannot. It's not good.
It is exact, Natalia. It's exact, because if you look at the surface, the fundamental domain for the surface, what do you have? You have 2g edges, right? You have 2g edges, and you have
Sorry,
2G.
if we have our surface construction, we have one face, 4 vertices, one face, 5, minus 18 edges. And
No. No, Natalia. We have 4 faces.
No, for the surface,
Right.
only we have one face.
No.
For me, your face is vertices. Okay, we have 4 vertices, but we have 4 faces, but we have 1 vertices.
No. Look, this what we were mentioned by these lines. This is 4 faces. They are lying one over each
4 faces,
other.
but we need.
We have 4 faces.
We need
No.
plus 1.
we have 4 faces, and they are connected. They are connected each time by 6 edges.
Okay, 4 minus 18 plus 1 is equal to
No, there is no one. No one. Only 4
Okay,
faces. 4 faces and 18 edges. That's all.
No, this is not equal to minus 2g. We have 1.
No one. No one.
I think is it not good?
No one. Because look, and you consider now. Don't.
Заклеить дырки чем-нибудь. Если у вас будут, это риббен-граф у вас получился, и чтобы получилось 2 минус 2g, у вас должна быть компактная поверхность. Нужно чем-то заклеить. Обычно мы заклеиваем вот этой вот одной гранью, граница которой и есть наша ниточка, наш узел. Вот ее не хватает, чтобы получилось 2 минус 2g. Вы не можете просто сложить вершины, ну или у вас грани,
Да.
вот, и ребра. Нужно еще чем-то заклеить. Ну, еще размерность должна быть 0, 1 и 2. И только тогда у вас получается 2 минус 2 компактная поверхность. Поэтому здесь что-то неправильно.
Нет, Наталья, здесь все правильно. Потому что это не узел, а это зацепление. И у поверхности, у поверхности край состоит из 2. То есть заклеивать надо не 1 раз, а 2 раза. Поэтому формула, because of this formula, which was in one component 2 minus 2g minus 1, right? Now this formula becomes this one, 2g, 2 minus 2g minus 2. So because of 1, if you consider now the fundamental domain for the Seifert surface with 2 components, this was maybe my fault that we were constructing the Seifert surfaces only for knots. But Seifert surface you can consider for arbitrary link for any components. If you have here 3, then here it will be minus 3 and so on. So
you are right, I see, yes.
Oh, okay. So what is our calculation? 2 minus 2g minus 2 should be equal minus 14. It means that our genus is equal to 7, right?
Yes.
So you see the surface, it looks like here I should put 1, 2, 3, 4, 5, 6, 1, 2, 3, 4. This is exactly our surface, only where I put the lines, there should be ribbons. Natalia, you are right. So, and then with these ribbons, you have the Seifert surface of genus 7. So there are 7 handles, 7 handles for this picture. Okay. Genus is equal to 7. Very good. Other questions, friends? Rafael, is it clear?
Yeah, it's clear. It's clear.
So
I
this
will
is
redo it. I will redo it myself, but it's.
Yes. So here, don't forget that if we construct fundamental domain for this surface, you have two components, and this change. So this is genus and two components, and this change the early characteristic and change the form. Two components, but it is possible. For example, if you have with n components, then you should have n in this formula, and this will be the early characteristic here. Very good. So this is done finally, and now we start. I'm trying to now, if there are no more questions, we start, sorry. We start, I need to sorry. Excuse me. No. So now we shall try to sorry, we shall try to this is previous one, so we shall try to prove the you see the next lecture?
Yes.
The theorem of group of torus knots. Do you see, Raphael?
I see.
Very good. So the theorem is that consider now the knot, the real knot. So R and Q, they are prime, not prime and numbers, but prime between them. So actually, it doesn't mean that they are prime, but only means I can write this in R and Q are equal to 1. Only this. So it may be, for example, Q is equal to 8 and R equal to 3. They are prime between them. So then we have the following formula. All the torus knots have this beautiful presentation. So maybe the proof is a little bit, it's not complicated, but if you never worked with Seifert-Van Kampen theorem, then we shall discuss this in details. So sorry, I raise this, and now I raise this, and I need this stuff. Do you see that I wrote that the sphere S3, which is 1-point compactification of our R3, can be decomposed with the two field torus. Is it clear, or I need to explain this?
For me, it's okay.
Prof. Natalia?
Okay.
I can try to do this. Say for example, I can explain this. Maybe it's not. So consider a torus, right? And let it be field torus. There is something inside of this torus, and there is a core of this torus, the line which goes through the center, say through the center. The torus is filled. Okay? So, and let us consider this line. Say it will be the XZ, right? And everything here we are living in our R3. Okay. Then consider now the complement of this field torus. This line lies in the complement. Now add infinity point. So this line will become a circle, right? Here somewhere there is the infinity point. And so it means that everything which is out of our field torus is also field torus. And this line is its core of this field torus. So this is the explanation why we have that it is we have this decomposition. This is our decomposition. S3 is equal to T plus T prime. This is, say, this is T and the complement is T prime. And they intersect by a torus as a surface. So F is a surface at the torus. So now there is in our sorry. There is here our torus knot. This is not now. We are not thinking about links. This is torus knot. We take a regular neighborhood. at the beginning of the course we were considering. So let it be regular neighborhood. Very, very thin, very, very small, but actually this is again a torus, field torus, but this torus is not a torus. Here this is unknotted, and neighborhood, tubular neighborhood around our knot is this is n. This is n. So let us consider what will happen. Consider the complement of this regular neighborhood of our knot in torus T. It's what it should be, what this should be. Now consider this regular neighborhood and how this regular neighborhood, it is also regular neighborhood of the torus knot in the surface of torus. But now let us cut our torus, the surface, with the help of this. This is the same as you are taking the torus knot or the complement of the regular neighborhood. So the question, if you now cut your torus by this torus knot, what do we have topologically? This is the question, and this is essential for us. Well, I maybe take away this picture, and the question is what it will be if we do this thing. What object do we have topologically?
Torus.
No, this is almost, but not. So, excuse me, what did I do? Right. So let us consider the following. So suppose now that our torus is smaller. This is because I need some place to make pictures. So suppose that our torus is this one. So so this is a torus, like this square is a torus. Now I'm cutting this thing. I'm cutting this torus by our knot. No, red is not bad, is not good. Red is already done. So by blue is done. So by green. Right. So I cut it.
Maybe cylinder.
Yes, exactly. But for the cylinder, from topological point of view, this is the same, what is called annulus. Okay? No, I'm badly. So this is, say, the space filled between two circles, right? Rafael?
Yeah, what is okay?
So how do we do this? So we cut, first of all, by this one, then we came here, and we cut by this line, then we came here, so sorry, by this, we come here by this one, and then we cut by this one, then we return back, we cut here, right? So now we have 1, 2, 3, 4, 5 sheets of paper, right? But we should glue them. Glue according to our for example, so let it be, this will be the basic sheet. Now, because how to glue better? How to glue better? Okay, so this piece we should identify. So this one we should identify with this one. So this we glue here. It means that we make sorry, like this, right? You see, so this is you glue here, and then so this we glue here, and then what we do next? Next, we put so to put somewhere here, we take this this triangle. Am I right? You put this one. Yes, you put this one here. So it will be here. This triangle we used. This triangle, this we used. And then we put also this one somewhere and this one, and you see, and then you make gluing somewhere here and somewhere here, and you have, sorry, it's not good, you have a ribbon, or you have a band. Topologically, this is the same as annulus. So essentially, that what do we have? This is the basic thing to understand. Rafael, did you understand that torus cut by the knot is nothing but annulus?
Yeah, for me it's okay. There is no...
Very good. So that's all. Actually, this is the basic thing that you need to understand, or for the proof that I propose. So now, yes. excuse me. I need to do this. Why it is not the good thing? Yes. So sorry. Right. So this is what I wrote in this way, that the complement of this small band or knot itself is what I denoted ARQ, and this is nothing but annulus. And this is what I wrote, the procedure which we were doing, which results from the air parallel strips on the cylinder being joined by the twist. So you can depict it by the cylinder, but anyway, it's annulus. The crucial thing is that if it is annulus, then it has the fundamental group the same as the circle, because if you have annulus, there is a center line. So you have, you have annulus, right? You have annulus and, and you have a circle, and you can deform your annulus to this circle. You make a deformation, and then you see that the fundamental group, which is homotopy invariant, you will have the same. And the fundamental group of this center line is Z, or as group theorists they write, they like notation, C infinity, cyclic infinite group. So this is the cyclic infinite group, right? So now now what is the this is it makes now you should think think about I erased now you have this torus, and there is the complement of this knot, and this is our torus knot, and our torus knot, and so this is, let it be the torus knot, where here, like, okay, there will be torus knot, and as we are going through this torus knot, we have this complement. Now we are taking away in the space, we are taking away the complement. So our aim is to study the fundamental group of S3 minus this N, this thickened knot. Actually, you can consider N as thickened knot. What do you see? This S3 minus N is equal to the first torus. This is our first torus field minus N, and union with the complement torus minus N. What these guys, T minus N, they are compact three-manifold. This is also compact three-manifold. Torus, field torus is compact. You are just taking a small knot in the surface. And intersection of these guys is what? The torus, which I noted, the surface torus, F minus N, and this is nothing but our bend, what I noted, A, R, Q. This is our annulus. Okay? So now look what is from homotopy point of view, what is this torus minus N? N make nothing effect on this. So torus minus N, topologically, this is the same as field torus. This is S1. This is the circle. The same way, T prime minus N, this is again S1. So because you just you take core of this field torus, and you see that it gives you the fundamental group. The fundamental group is the generator. So the fundamental group of this union, we are calculating using the fundamental group of parts. So the Raphaël, so par morceau. Raphaël.
Once again?
Vous avez deux morceaux.
Mm-hmm.
Notre but est regarder Sn moins n. D'accord?
Mm-hmm. Mm-hmm.
We decompose it in two parts. We have decomposition of S3. Now S3 minus n, we decompose in two parts. Deux morceaux. This is the torus minus thickened knot, and other torus minus thickened knot. Look how these two parts intersect. They intersect exactly by these, what we were constructed by cutting and gluing. This is, so each torus has its own generator for the fundamental group. Say this has A. This is A for this torus. for other torus, this is B. Let it be this our line.
Yeah.
And now you need to understand that this generator, when it is mapped to the no, better to say like this. So let us consider our annulus. This is a circle. This is a circle, and it has its own generator. We denote it, say, by C. And this annulus, it is mapped to the first torus and to the second torus. This annulus has its own line. We note it by C. When we put this intersection to the first torus, C is mapped to R to the power of R. This you can see when you were gluing and cutting the paper, and when it is mapped to this torus minus N, you see that C is mapped by the B to the power of Q. And if you remember, I wrote down for you the one-Kampen theorem that the fundamental group of the space, which is divided on two parts, is given the same way, that generators are the generators of each part. This is A and this is B, and then you need to take into account the intersection.
Yeah.
And this gives you exactly the AR equal to BQ. So this is the standard proof. I don't know whether I explained it more or less carefully, but anyway, I tried to write down it absolutely carefully. Maybe my explanation plus what I wrote, this is more or less gives you more or less some explanation. So Natalia, do you have questions?
No.
Really? This was the hardest part of our... Sorry? I'm listening for you, Natalia.
Maybe I need to think about it more.
Yes. So the main thing that is based on what you perfectly understand. That picture that I draw, how we construct this band, right? Now look how the generator of this band, this will be the center line of this band, how it is mapped to the generator of the first torus and generator to the second torus. This is exactly what I tried to answer the Raphael questions at the beginning. What does it mean? How many times? When I counted the number of intersections with in these directions and in this direction. So actually we counted how many times this C going around A and going around B. Right.
Okay. I see that A and power R and B power Q is equal, but this is not equal 1.
No. No. This is no.
Only
Yeah.
one equals. Yes.
Yes. You cannot shrink. You cannot shrink if you go r times here or r times here. You cannot shrink it to 1. Yes, but
I see.
okay. Very good. Then what do we have next? I just look at the notes. So this is the interesting theorem. So this is this form with the generators and relations, and this form with the in the product with amalgamation. So I wrote in this way, but maybe some of you are more accustomed to the following form. So this is this is ZR, this is ZR star with Z, sorry, what Natalia is saying, I took the same as equal to 1. No, Z, sorry, excuse me, Z amalgamation with Z with U R is equal to V Q. So this means how these two groups are joined. So it's yeah. So so we shall in a moment today we shall study the braid group, and for example, Natalia, please look at the simplest example, A2 equal to B3, right? This is for torus. And this is the same as the braid group. This is the same as the braid group, which in other generators have the form which you will see in a moment. And in a braid group, this is a braid group on 3 strands. And in a braid group, there is no element of finite order. So the simplest case, A2 equal to B3, if you will put that this equal to 1, this means that in your group, there are elements A2 of order 2, element B of order 3, but for braid group, it is known, this is one of the basic facts, that in the braid group on 3 strands, there are no elements of finite order. Okay. So this amalgamation is quite large. It is not so it's quite big group without element of finite order. Okay, so now I think that is what we proved. At least I wrote down and gave indications. Then that what we don't prove in details, but I just say something. Sorry, too many garbage. Okay, this is the proof. And now I'll leave this without a proof, but just can make you some words, tell some words that from this presentation, from this formula, and some group theory, which we don't actually we don't need to do more, but some group theory will give us the proof that torus knot is prime, or if R and Q they are prime between them, so it's a coprime in English. So then each torus knot is prime knot. So in particular, this means that we have an infinite family of prime knots. Of course, they are much larger than TRQ, but it's enough for us because our theorem, we make the statement of the theorem that the semigroup of knots is the same as semigroup of numbers with respect to multiplication. So now we can make these precise arguments. So the number of prime knots is infinite. Actually, it is not more than countable. For example, you can see that there is a finite number of knots at each with fixed crossing number. So we have countable number of prime knots, and so we can make the one-to-one correspondence between prime numbers and prime knots, and this is commutative, so we have isomorphism as semigroups as monoids. So monoids of positive integers with respect to multiplication is isomorphic to the semigroup of knots with respect to connected. So this is proved, and also we can just without proof can mention the following theorem, that the unknotting number and the genus of torus knot is equal to this number. So right, so for example, but for the as far as I remember, let us correct me if I'm not right, so I didn't wrote it. So R minus 1 Q minus 1, and then plus 1 plus 1 minus n divided by 2. This is the same thing. The unknotting number and the genus for the link Not, this is for torus. When they R and Q, they are coprime. So this is one component and n equal to 1. And this formula is for link. Do you understand?
Yes.
Natalia?
Yes.
So if I am correct, then let us look. What do we have? What do we had in our exercise? 4, 5, no, 6, but I wrote 5, 6 minus 1. So it will be 3 multiplied by 5 plus 1 minus 2, because it is 2 component, and divided by 2. So what do we have? 15, 16, 14. In our case, we have 7. This is what we calculated. So it is very close. So Natalia, this is for your argument that by Seifert surface constructed by hand, we obtained the genus.
Okay, I see. Thank you.
So what we constructed by hand, our Seifert surface with, you remember, 4 plates and 18 edges, this gives us 16. So actually we constructed the minimal genus. We constructed the minimal genus. So you are right in the sense that in many cases that Seifert surface gives you actual genus. I can also mention something which gives you argument. There is a following theorem, but the proof is complicated, that if you have alternating diagram, then the Seifert surface of this alternating diagram give you the actual genus of the knot and link. So it means that, for example, the diagram that I gave you by picture, it's alternating diagram, and it is the argument that we actually get this thing. So, and the example, if you remember the example that we had like this, and there was something like this, when we were getting the difference of the genuses in the genus of the knot and genus of the Reidemeister surface, it was not alternating diagram. But so if you want to have if your knot is alternating, you should try to write down the alternating diagram, and then, Natalia, you're right that you get all the time, you get the genus, the real genus of the knot. So you get a minimal genus of all the possible surfaces. And as we saw, I forgot exactly the number, but it is somewhere with 8 crossings that the first non-alternating knot we meet. Okay, so this is about, and this part, I think, about unknotting number is also very difficult. So the But this is a real proof. So now you have this exact meaning of unnoting number for infinite family of nodes. Okay. So as we mentioned above, it is simple to define the invariant like unnoting number, but it is difficult to decide. So it's one of the rare cases when you can give the exact value of the unnoting number of the infinite family of nodes. Okay. Are there any question? I think this is for this part of the lecture. It's all. We shall start other stuff right now. Yes. Other questions?
No, it's okay.
So this is more or less. This is not directly connected with nodes, but maybe it's. If you don't know about this, then I can tell you, and I use this as arguments for the next notion that we shall study. So the then fundamental problems. Did you hear about these problems, Rafael?
No, I haven't. Maybe when we read it, maybe it will remind me something. But so far,
very good. So the idea may be the following: that we constructed, we have a node link, we have diagram, we have Reidemeister move. By diagram we construct presentation. We can construct a group. A group is a wonderful object. So we transferred the problem of distinguishing nodes to groups. So we reduced our topological problem to algebraic problem. Even modular the fact that in our exercises we understood that group does not resolve all the problems, but still we see that it is quite powerful invariant. So maybe we've done a lot when we construct a group for our node. So maybe it's okay, but unfortunately the distinguishing group is also difficult problem. So we reduced in some sense difficult problem of understanding nodes to not easier problem to distinguishing nodes, distinguishing groups. So for example, let G be a group given by means of some presentation. Suppose that we have finite even presentation. So you have another group, and also given by another presentation. The simple question is, for example, you have the group G. You have for one node. You have one diagram, you have another diagram, and you don't know whether they are the same. So you construct a group for the first diagram. This is what you can. You can do Vertinge presentation for one, Vertinge presentation for the second one, and you want to decide where these two groups are the same, isomorphic in the language of group theory. But it is not so simple. It's there were after then in the 20s formulated these problems, but then it turned out that in general for all groups in classes of groups, these problems are non-solvable algorithmically. So to distinguish for arbitrary groups given by arbitrary representations, even finitely presented, it is not algorithmically solved problem. So there are, of course, simpler problems. For example, if you have a group and in this form it is the following: you write down the word in the generators of G, and to decide after finite number of steps whether this word is give you the identity element of G or not. So you have arbitrary word. You should decide whether it is identity or not. This is the same as to say you have two words in the same group, W and V. So you have two different words in the same generators, but the words are different whether they give the same element or not. And this is the same problem, because you can write down another word, and you can make a question whether it gives you, it is the same as whether WV minus 1 gives you 1. This is the same as to decide that the word W gives you the same element in the group as the word V. So this is the word problem, to understand whether these two different words give the same element of groups. Another problem, dense problem, is whether to decide that two words, W and W1, gives elements which are conjugate. So say that the elements, whether they conjugate, so you have the element A, and whether there exists an element C that, no, say this A, and this C, this is D, C minus 1. So decide whether two words give the same, not the same, sorry, the same is the word, but give the conjugate element in the group. This is the conjugacy problem. Of course, it's more complicated than the first one. So this is the fundamental algorithmic problems in the group theory. So we shall need these notions when we shall look at the braid groups. And now we just mention very simple thing that in some cases this is solvable. These two problems have algorithmic solution. This is the free group. We also need this for when we'll study the braid group. So we say that a word in the alphabet A, where alphabet is such that A minus 1 is present, is reduced if there are no words A epsilon, A minus epsilon. So this is the same as that there are now subwords here, A minus 1, or A minus 1, A. This is reasonable that the word is reduced. If there is so, you can just eliminate them both, and that's all. So this is the reduced word. Now, what is the solution of the word problem for the free group? So each element of the free group, let free group F, lambda, and lambda be the arbitrary how to say, arbitrary cardinality, not necessary. Of course, we work with finitely generated, but the theorem is the same, so I wrote it down for arbitrary. So you have arbitrary alphabet of arbitrary cardinality, and then you say that for each element of free group has a unique reduced form. That is, each word is equivalent to reduced word, and it can be done algorithmically. So better to do this with example. Say, for example, you have. I'm sorry. Sorry. Do you see the screen?
Yes.
Yes.
You see the theorem? Not the
Yes.
pictures? Very good. So say you have a word. Say you have a word. A, B minus 1, C, D minus 1, A minus 1, right? So imagine now that you are computer. You are computer, fancy notebook. So what do? You start to read this word. I bet formally, if you don't like this word computer, you are Turing machine. And then what I'm saying is exact. You are Turing machine. What you are doing? You are writing the first letter. It's A. Then you are writing the second letter. No. You are looking for the second letter. If the second letter is the inverse of the first one, you erase both of them and you continue to do. Here, B is not the inverse of the previous, then you add it. It is A, B. Then you look for the next one. This is B minus 1. We are in the situation that B minus 1 is inverse of B. So it means that you erase the, sorry, it's not the algorithm, it's my fault of writing. A is erased by B and B minus 1 is erased. Then I'm looking the next one, C. C is not inverse of A. I write C. Again, C. D, I write D and D minus 1. So I need to erase this one. Then I have A minus 1. A minus 1 is not equal to C minus 1, so it's This is the reduced word. And you see that because the length of the word is finite, this is a real algorithm, it's finite procedure. So this is the reduced form, and you can make any word to the reduced form. And the algorithmic solution of the word problem is the following. You have two words, W1, W2. You put both of them to reduced form, and you just consider, again, you are Turing machine, you consider letter by letter these two words. If they coincide letter by letter, then you see that they are right equivalence, equality, but this is not equality by words, it's equality as element. So then it means that they represent the same element in a group. So you see that very simple solution of the word problem for the free group. Okay, then sorry, again, I'm stupid. So again, what was our word? Our word was A, C, C, A minus 1, right? So what do you see in solution of the conjugacy problem? It is the following. The word is cyclically reduced. If it is reduced, of course, and then there is no situation like here, A and A minus 1. You should erase both of them. So, and this actually gives you solution. First of all, you make your word in reduced form, like this. And then you are Turing machine, you are looking at the first letter of your word, and this is a finite procedure. You are looking the last letter of your reduced words. If they are different, it's okay. But if they are in the same situation, then you should erase the first one, and you should erase the second one. So now you see you should continue this procedure. What do you see? The first letter is C, the last letter is not C minus 1. So this is cyclically reduced word, and this is the finite procedure. So you see that the free group has very good solution of this algorithm. Other questions?
No, it's okay.
Natalia, do you have a question?
No.
Very good. So now we finish with this, which was a little bit too. Oh yes, I wrote down. Sorry, I forgot that I wrote down this example, but maybe it's better. Sorry, I wrote down this. I wrote down, but anyway, it's better. I wrote down it's just a week ago, and I forgot that I wrote down. But anyway, it will be, if you forget my explanations, you can read down all this formal stuff. And now, all of this was the prerequisite, and now the essential thing is the following, that it is difficult to deal with groups, so we should reduce information from groups to some other stuff which is more easily to deal with. And one of these is the Alexander Conway polynomial. So it was quite a long story how to obtain this polynomial. One of the way is that you, with some procedure, constructing some matrices, ideals, determinants, starting from the group of a knot, Vertinge presentation, and you get a polynomial. But we don't have time. But only I can tell that all the information that is in the group, not more, you can, not all, sorry, all the information what is in polynomial, it is contained in the group, but maybe it's not so simple to extract. Unfortunately, as we are making this course still in the COVID situation, John Conway, who was the final author of this polynomial, final form that I will tell you, he died out of COVID-19 in April. So this is a very sad situation. He was a great mathematician and made a big impetus for knots and especially for group theory. Okay, so this is the Conway form. Alexander was the first in 20s, and Conway in 60s gave the final, very, very well-known and very beautiful form for this polynomial. So you can give it by axioms. So we don't have time to reduce everything by just axiom. So to each oriented knot or link, we associate a polynomial. Polynomials say variable z. And this is invariant. This is nothing but expressed invariant. It means that if two knots are equivalent, then the polynomial are exactly the same as polynomial. This is the initial condition, that if this is a knot, you put for simplicity very simple polynomial equal to 1, the second axiom, and maybe the first, anyway. So, and then you have this, which is called Skene relation. Skene relation, and this word is exactly, so John Conway was British, I think, and this is the British word, skein, which comes from the piece of wool from a sheet. So, Raphael, do you know how it is translated in French, skein?
I have no idea.
I also forgot, because, you know, the French mathematicians never use it, they use skein, of course. They say relation de skein, but there is translation. Probably it is entortillement.
Wouldn't make sense. Yeah, it wouldn't make sense.
If you want, you can look in the vocabulary and give me. So it means, I think in English, it means something like this, the piece of wool, something like this. If you have a sheep, and then if you have some which is in this form, that it is skein. So you'll see how we'll use this to do something. So what does it mean? This is the knot diagrams. Actually, this is the pieces of knot diagram. You are looking by the microscope at your diagram. It may be very complicated, many million of crossings. And you are just looking by microscope and you see only one crossing of this type. If you remember when we were calculating the, how to say, linking number, we were calling this +1. This was -1, and this is smoothing. So it means that our node diagram is the same, exactly the same, but exactly what we see in the microscope. So if you exclude this, your diagram is the same. So in reality, we have links diagram here. We depict only small parts of it. So L is a real link. So this is L, complicated L plus. This is L minus, is the same, but here, and the same here. And this is the John Conway's wonderful skein relation. So in the skein, you means that if you have complicated, you may, I don't know how to say in English, maybe diskein or something like this, that the Conway polynomial of this one minus the same polynomial of this link will give you the unlink in this, the smooth link, better to say, in this point, multiplied by Z. This is the skein relation.
So wait, you mean that if we make all the crossing, overcrossing minus making all the crossing over undercrossing, it equals to Z times the smoothing of all the crossing?
No, no.
No.
Absolutely,
No.
au contraire.
Okay.
You change only in one. So I maybe explained,
okay.
You change only in one. Or you like, if you want to shoot, you are with a gun and you see in your ocular, you see the small piece where this crossing is. You are shooting only here. Your deer doesn't touch. Crossings became the same. So you have chosen this small piece and you are making changes only there.
Okay.
Everywhere, but here the crossings rest intact.
Okay.
Okay. So L is a real diagram of which we called L plus. L minus is the real diagram with millions of crossings, which are all the same, but -1. And here you have -1 crossing. You see that number of crossings here is the same. Only the crossing change. But here the number of crossing is n -1. You made one smoothing. Okay. You'll see in example, if you give me 5 minutes, I'll finish it because it's not good finish. Finished in definition, not an example. So we say that the link is split if its diagram contains two non-empty parts. The theorem is that if the link is split, then the Conway polynomial is 0. In particular, if you have n component link, then this is 0. This is very simple to prove. I prove it in a moment. So what does it mean that your diagram, that your link split? Of course, it means that you can have the following diagram. You can have the following diagram. So in this box, you have your link L is L1, and in another box, you have your link is the same. This is simply another part. This is L2, right? So you put, and you're trying to make some kind of some kind of, how to say, connected sum, but a little bit strange manner. You making, say, this one and that one, okay? And this is the same, L1, only I have not big space, but this is the same. This is L2, and you are making in opposite direction. You make not direction, but plus crossing to minus crossing. Okay? You see that they differ, that this line goes this over, and here it's under crossing. But you see that this is the same. You can simply, in space, make rotation by P. Right? This is the same. Right? Rafael?
Yes, it's clear.
This is the same. But if you are not making this strange procedure, you have here just L1. I don't have time to do. This will be smoothing like this. Here you will have your own L2, and this is like this. So what does it mean? That polynomial of this minus polynomial of this, but the polynomials are the same. So it means that the Conway polynomial of this is z times 0. So it means that if your diagram is split, you have 0. Okay? Natalia?
Yes, it's clear.
So this is a wonderful fact that, for example, if you have unlink of n components, it's not true for the link, even Hopf link, but for unlink you can divide and you have 0. So Conway polynomial have value 0 if you have two paths. This is what we shall use immediately, and I give you the of course our trefoil. This is our left trefoil. This is a point, maybe, sorry, I make it bigger. It's better? So I look here and I make, so this is the answer of your question, Rafael. We are making changes only in one point, only in one crossing, here. This is our knot. We made this crossing. We made this crossing. Crossing change, better to say. It was, this line was going under. You see, this is going over. We changed to this. This is evidently because one crossing, this is a good thing. You have one unknotting number. You get a circle. But here you should make smoothing. You made a smoothing here. So the polynomial of here is equal to 1 plus z times polynomial of here. And here again, but now in this point. This is okay, you came to the end. But in this point, you should, because there is a crossing, you should again make Conway-Skene relation. What do you mean? You have one crossing change give you two circles, as we just noticed. This is 0, and smoothing here again give you this curly circle. this is our circle. So what does it mean? Now to calculate what do you have, I'll write down here. This is 1. You have crossing change here. Here you have smoothing. You should have Z. Here you have again smoothing Z. Here you have 1. So what is the, sorry, what is the, no, it's a bad idea. Yes. So what is the polynomial, Conway polynomial of Trefler?
Uh, 2 minus 2z equals 0? No?
1. This is 1 plus Z times Z squared.
Ah, okay. Okay. Ah. So wait, it's Z times Z plus 1, no?
No. 1 plus
No.
Z squared. Okay, look here.
Yeah.
Is
So
equal
take...
to 1 plus Z multiplied by here. This is negative. This is negative crossing. But anyway, they are of course in the all the time they are in the opposite. If you have negative, and you can always put them in different paths. So this one should be 1 multiplied Z by something. And something will be again Z multiplied by 1.
Okay.
Very good.
Okay.
So the same way, the next one, figure 8, the same procedure. The same procedure for our favorite next stuff. Sorry. You took this one. What do you have? For example, I didn't put the orientation, so I put it down now. Let it be. Okay, sorry. Let it. Sorry. I don't know why it is. Right. So let it be this direction, like this one. Right? Am I right? So this is plus. It means that here 1 is okay, but here Z goes with the sign minus because no, plus. No, it's plus. Sorry. No, sorry. Here we have minus. So here again plus, because it is positive. It is positive, right? It is positive. Then we put negative to this one. It will be Z multiplied the Z with this one. But this is links. This Hopf link, and if you now put here, you have minus Z. So here we have, you can, I don't have much time. Here you have 1 minus Z squared. You see how it works. And, so if I remember, this is called tree for the resolving tree or something like this. The tree I remember. So Natalia, if you like graph theory, so this is a graph, or this graph is tree for making resolution. And you can think, for example, at the question. If you will not give an answer now, then it may be the homework. Why this process always has the solution? So you start with arbitrary knot, and you can construct this tree, and which give you the resolution of the for the knot, say for the knot, right?
Well, if we at some point we either always make an overcrossing, so at some point we will make an overcrossing of all the crossings, so it will give simply the unknot, and on the other hand we also smooth the crossing each time. There is a dichotomy between making all overcrossing and then smoothing. So for sure we will get to an end.
Right. Exactly. What you are saying, this is absolutely solution. Only small remark: you should, to formalize this, you should use the induction by recurrence.
Yes,
so you mean that you take the arbitrary diagram. We were looking, and there was maybe even I don't know. Yes, it was maybe homework, but we explained it that.
Yeah, we did something like that with
arbitrary diagram. You can go higher, and then you can fall down. Finally you can get a knot. But here, for example, you take arbitrary knot with n crossing, and you know that when you changing crossing, you obtained simpler, or you obtained with n-1 crossing. By induction, n- crossing is okay. Simpler, you can finally continue this process, and you finally get the unknot. Yes, exactly. So it will not be the homework. It is always done. So for any knot, you can make this resolution, and so on. Right. So sorry for I was late today. If there are any questions, I'm happy to discuss your remarks and questions. No questions?
I think I sent you an email. It was about, so we can write notes in the stories. But what about, for example, writing them in plain battle, or if it makes sense or not?
Sorry. I forgot about this, and actually I didn't think a lot. I have only the following remark. I have the following remark that maybe it's nothing. So we have so knots is something what is saying us about R3, right? So we have torus, and you can embed torus in R3 without singularities and so on. but you cannot embed the clean bottle, surface of clean bottle in R3 without intersection. This is the result of embedding theory. So, and then, so if the surface itself intersects, so you may obtain intersection if you just write your knot like in the sheet of paper, clean bottle as a square, it will be no intersection. But when you consider clean bottle in the R3, it has intersection. So maybe your knot will have intersection. So it will be some object which is called a knot with singularities or something like this. So this is just a preliminary remark about this. But knots in three manifolds, which of course are not embeddable in three. This is a huge field of work, but of course it's much more complicated. Even in R3 we have, but in it's a huge work, and it's sometimes even more interesting when you are considering knot for surface. I know that for example, if you have surface and you make a surface product with interval, this will be object of 3 dimension, and you can put the knots here, and it in some sense it is even more interesting because you have connection between your 3 manifolds and knots. So in some sense, if you consider many knots embedded in your 3 manifold, then you can say something about your 3 manifold. So it's very interesting and complicated field of work. Okay?
Okay. Okay.
Thank you.
Thank you.
Goodbye.
Bye. See you next week.
Goodbye. Thank you.